Archimedes was sitting alone, thinking. Around him, Syracuse was preparing for war. The city was under threat from Rome. Soldiers moved through the streets. Ships filled the harbor. Weapons were being prepared. The sound of metal, footsteps, and shouted orders carried through the city. But inside a quiet room, Archimedes was focused on something else. In front of him was a simple drawing in the sand. A circle. Then another circle inside it. Lines crossed the shapes. Numbers filled the space around them. To most people, it might have looked like meaningless marks. To Archimedes, it was a question. How could the size of a circle be measured exactly? He had spent years asking questions like this. How does a lever work? Why does an object float? How much water is displaced by a body? How can the volume of a strange shape be calculated? How can a small force move something enormous? And sometimes, the answer began with something very simple. A stone. A piece of wood. A bowl of water. A balance. Or a line drawn in sand. Archimedes lived more than 2,000 years ago, yet some of his ideas still sit quietly inside modern mathematics, physics, engineering, and science. His story begins in the ancient Greek world, in the city of Syracuse. Syracuse stood on the island of Sicily. It was a wealthy and powerful city, surrounded by the Mediterranean Sea. Ships arrived carrying goods from distant lands. Markets were busy. Builders raised walls and temples. Sailors watched the sky to guide their journeys. And scholars gathered to study mathematics, astronomy, philosophy, and nature. Archimedes was born there around 287 BCE. We do not know every detail of his childhood. Ancient records about his early life are limited. But we do know that he grew into one of the greatest mathematical minds of the ancient world. At some point in his life, Archimedes traveled to Alexandria in Egypt. Alexandria was one of the great centers of learning at the time. Its scholars studied mathematics, astronomy, medicine, language, and philosophy. There, Archimedes could meet other thinkers and study the work of earlier mathematicians. He learned from the mathematical tradition that had been developing for generations. But Archimedes was not satisfied with simply reading what others had discovered. He wanted to test ideas. He wanted to know why things happened. And when he found a problem, he could stay with it for a very long time. One of his greatest interests was geometry. To Archimedes, geometry was not just a collection of shapes. It was a way to understand the physical world. A circle could become a problem about measurement. A triangle could become a problem about distance. A solid shape could become a question about volume. And a simple lever could become a lesson about force. One of his famous ideas involved the lever. Imagine a large stone lying on the ground. It is too heavy for one person to move. You push. Nothing happens. You push harder. Still nothing. Archimedes understood that the problem was not only strength. It was position. With the right lever and the right place to apply force, a smaller force could move a much heavier object. The longer the lever, the greater the mechanical advantage. The basic idea is simple. But it changed the way people thought about machines. Archimedes is traditionally associated with a famous statement about the lever, give him a place to stand, and he could move the earth. Whether he actually said those exact words is uncertain. But the idea captures something important about his thinking. He understood that a small change in position could produce a huge change in effect. That same way of thinking appeared in his work on floating objects. One of the most famous stories about Archimedes begins with a crown. The story was recorded centuries later, so historians cannot know exactly how much of it is true. According to the story, the ruler of Syracuse, King Hiero II, had ordered a gold crown. He suspected that the craftsman had secretly replaced some of the gold with a cheaper metal. But how could anyone test the crown without damaging it? The problem reached Archimedes. He needed to determine whether the crown was pure gold. He could not simply melt it down. He needed another method. Then, according to the famous story, Archimedes entered a bath. As he lowered himself into the water, he noticed something. Water rose around him. The amount of water displaced depended on the volume of his body in the water. Suddenly, he saw a possible solution. The story says he became so excited that he ran through the streets shouting that he had found the answer. The famous phrase is usually remembered as Eureka, meaning I have found it. The details of the story may have been simplified over time, but the scientific principle behind it is real. An object placed in water displaces water equal to the volume of the part that is submerged. And a floating object experiences an upward force related to the weight of the fluid it displaces. This became known as the Archimedes principle. It is still taught today. Think about a ship. A huge steel ship can float even though steel itself is much denser than water. Why? Because the ship is not a solid block of steel. Its shape allows it to displace a large amount of water. The water pushes upward. When the upward force balances the ship's weight, the ship floats. Archimedes had found a way to connect mathematics with the physical world. But his curiosity did not stop with water. He also studied geometry with remarkable precision. One problem fascinated him for years: the measurement of the circle. Everyone knew that circles were related to a special number now called pi. But how could its value be estimated? Archimedes developed a clever method. He placed polygons inside and outside a circle. Imagine a circle surrounded by a shape made from straight lines. The more sides the polygon has, the closer its shape becomes to the circle. Archimedes used this idea to place limits on the value of pi. His calculations were astonishingly accurate for his time. He did not have modern calculators. He did not have computers. He did not even have modern mathematical notation. He had geometry, careful reasoning, and patience. He could turn a difficult problem into a series of smaller problems. That was one of his greatest strengths. He also studied the volume of spheres, cylinders, and other shapes. A sphere inside a cylinder fascinated him. He discovered an important relationship between their volumes. The result was so meaningful to him that, according to later accounts, he wanted a sphere and cylinder carved on his tomb. Again, some details of ancient stories are difficult to verify. But the mathematics behind his work is clear. Archimedes was pushing geometry toward a new level. He was beginning to use methods that resemble ideas later developed in calculus. He could think about an object by dividing it into many smaller pieces. Then he could use those pieces to understand the whole. It was a powerful idea. Centuries later, mathematicians would build much more formal systems from similar thinking. But Archimedes also had a practical side. He was not only interested in abstract mathematics. He designed machines. One of the best known is the device now called the Archimedes screw. It was designed to move water from a lower level to a higher one. Picture a large tube with a spiral inside. As the screw turns, water is carried upward. Simple, but useful. Similar screw mechanisms are still used in different forms today. Archimedes also studied pulleys, levers, gears, and other mechanical systems. He understood that mathematics could become a machine. And Syracuse needed machines. The city was becoming caught in a larger conflict. Rome was expanding across the Mediterranean. Syracuse had connections with Rome, but the political situation changed. Eventually, Rome attacked Syracuse during the Second Punic War. The city prepared to defend itself. This is where Archimedes' work took a dramatic turn. The mathematician who spent years studying circles and spheres now found himself helping defend a city. Ancient writers describe powerful defensive machines designed under his direction. Large catapults could throw stones toward approaching forces. Mechanical devices could help move heavy objects. Some accounts describe cranes or claw-like machines used against ships. Other stories describe enormous mirrors being used to set Roman ships on fire by focusing sunlight. That particular story is widely debated. There is no strong evidence that such a weapon actually worked in the way later stories describe. But Archimedes' other defensive machines are much more believable and fit the engineering knowledge of his time. The Roman attack was difficult. Syracuse was protected by strong walls and by its geography. For a time, the Romans struggled to take the city. Archimedes had turned mathematics into defense. But eventually, Syracuse fell. In 212 or 211 BCE, depending on the chronology used, Roman forces captured the city. The exact circumstances of Archimedes' death remain uncertain. One of the most famous accounts says that a Roman soldier found Archimedes working on a mathematical problem. He was drawing figures in the sand. The soldier ordered him to come with him. Archimedes refused. According to the story, he wanted to finish his problem first. The soldier became angry and killed him. It is a powerful image. An old mathematician standing beside a drawing in the sand. A city falling around him. War outside. Mathematics inside. But historians cannot know exactly what happened. Ancient sources give different versions of his death. What seems clear is that Archimedes was killed during the Roman capture of Syracuse. He did not live to see the full influence of his work. And perhaps that is one of the strangest parts of his story. He lived in a world without modern science. There were no laboratories like the ones we know today. There were no universities in the modern sense. There were no computers. No microscopes. No satellites. No spacecraft. Yet he asked questions that still matter. Why does something float? How does force move an object? How can we measure an irregular shape? How can we estimate the size of something we cannot measure directly? How can mathematics describe nature? These questions did not disappear with him. They traveled through time. His work was copied, translated, studied, forgotten in some places, and rediscovered in others. Centuries later, European mathematicians studied his writings again. Scientists and engineers found new uses for his ideas. His work on buoyancy became part of physics. His work on levers became part of mechanics. His geometry became part of the history that eventually led toward calculus. His approach to measurement influenced the way mathematicians thought about area and volume. And his machines became examples of how mathematics could solve practical problems. But perhaps the most important part of Archimedes' story is not a single invention. It is the way he looked at ordinary things. Water was ordinary. A stone was ordinary. A lever was ordinary. A circle was ordinary. A floating object was ordinary. But Archimedes could look at something ordinary and ask an unusual question. He could stand beside a pool and see a problem in physics. He could look at a circle and see a mathematical challenge. He could see a heavy stone and think about mechanical advantage. He could watch water move and imagine a machine. That kind of curiosity is easy to underestimate. We often imagine great discoveries as sudden flashes of genius. But Archimedes' work shows another side. Discovery can be slow. It can involve repeated mistakes. It can require drawing the same shape again and again. It can mean asking the same question from a different angle. And sometimes, it means sitting quietly while the rest of the world is busy. More than 2,000 years have passed since Archimedes walked through the streets of Syracuse. The buildings of his city have changed. The machines are different. Our ships are larger. Our mathematics is far more advanced. We can send instruments beyond Earth and calculate the movement of planets with extraordinary accuracy. Yet when a modern engineer studies a lever, when a student learns about buoyancy, or when a mathematician measures the area of a complex shape, a small part of Archimedes' intellectual world is still present. His life reminds us that science does not always begin with complicated equipment. Sometimes it begins with noticing something, then asking why, then refusing to stop until the answer becomes clear. Perhaps that is why the image of Archimedes drawing in the sand has survived for so long. It captures something simple. A man, a question, a few lines, and a mind trying to understand the world. Outside those lines, an army was approaching. Inside them, Archimedes was still thinking. And even after he was gone, the questions continued. The circle remained. The water remained. The lever remained. The stars remained. And the search for understanding continued.